Good morning, fellow Eterna developers. Today I'm going to be presenting the documentation and code for the new 3D version of Eterna. So first off, let's see. So first off, when we're developing the game and we're pushing up new versions, since the entire game is written in JavaScript, all of the functions and variables are in this global namespace. So this means that uh, pretty much all of the game code is in this one file called game.js. And additionally, since when we're developing for the web, we need to minimize the amount of space that's used. Uh, Published versions, final versions that are not just for development, should use a minified version of game.js. So what I mean by minified is that instead of using long and meaningful function names and variable names like get motif ID, it'll switch them to something like function A. So you can just search JavaScript minifier if you want to develop and publish, and any of these links should be fine. So most of the game code is in this game.js. Puzzle.ping is the image right here. Ball.ping is for when you're displaying atoms. Styles.css is for all of the styling for the GUI elements, the HTML elements here. Unique motif data is the pre-computed Ghost solutions, these. And then motifs contains the actual PDB files. And you also have the main HTML file in the themes folder. So I've split up the functions and variables into 8 different groups. We have RNA objects, so everything related to the PDB files, RNA elements. Loading and parsing data, that's everything related to reading in and analyzing the PDB files, DSSR files, and reference frame files. Manipulating atoms, these are utility functions, for example, calculating the distance between atoms, etc. Ghost motifs and hints, these are all the functions for the pre-computed solutions, those are these. Secondary structure and sequence generation, so these are currently buggy right now, they're a little hacky, so right now the documentation is not up to date and the code itself needs to be reworked, but this is still everything related to generating those two. Matrix manipulation are utility functions for dealing with matrices. Game objects are everything related to the objects inside the game, the 3JS objects. And then game display is when we're displaying the game using 3JS. So let's start off first with RNA objects. So as I said, this is anything related to analyzing the RNA data. So first we have this class called PDB parser. So this is a class that I made and then added to the 3JS library. And if you're just developing locally, then you should be able to find it in JavaScript/PDB parser and then the version number. So it just contains all of the functions and information for parsing and loading motifs. And it loads in the PDB file, the reference frames file, and the DSSR.out file. And it converts this into 3JS objects and normal data arrays. So you can just initialize by using the new operator, and then there's 2 important variables. The first is load bonds. This decides whether or not you should load the bond statements in the PDB files. And create bonds, this decides whether or not it should parse the PDB information and make bonds respectively. So for example, inside a guanine molecule, there are no bond statements in the PDB file, but if you enable this to true, then it will still make those bonds. And then next we have the residue object information. So the residue object takes in a name. This is the residue name and then the residue number. And it also takes in the what is it called? It also takes in what kind of residue it is, a guanine, cytosine, adenine, or uracil. And then it also has a variable that stores the atoms. So if you're making a new residue, you can just use new residue and then the type, guanine, cytosine, adenine, or uracil, and then the residue name. And then you can just add to the atoms array. Next is base pair. This is another object, and it represents the connection between two residues. So it takes in the two residues. These can either be the strings or the actual residue objects. And then it takes in the rotation matrix and the center from the reference frames file. And in the code, initially they're set as strings in the PDB parser, but they later become set as residue objects in the main file, and once everything is loaded. Next is PDB model. So this was originally used to store the various model commands inside a PDB file, but now since we're only using the first model in any PDB, this class is useless. Next is motif entry, which stores all the information loaded from the pre-computed solutions, the data file, and it has no methods. It just initializes everything on one go, and it's just to make going through the motif entries easier. Next, we have the model inside the main code. So this just holds all of the game objects that we're using to display the game, the 3JS objects. So for example, we have the 3JS geometry, we have the particles, we have the collision spheres, and the various materials for the bonds, the backbones, and the main atoms. And it also has other information like the ends, the residue objects, and the parsed DSSR information. So next is the category about loading and parsing data, so PDB files, DSSR files, and DAT files. So first we have the load file function, which just calls in the load AJAX file function on the PDB file, the DAT file, and the DSSR file. And this function takes in the URL to the PDB file, and it automatically parses that to get the URL for the reference frames file and the DSSR file. And it also takes the callbacks for the PDB, the DAT, and the DSSR. And then next is the parse DSSR function. So this just goes through the DSSR file, looks for the specific statement, list of n base pairs. So a DSSR file looks like this. So most of this information is useless except for right here. We need this statement and this statement. So it looks for this, and then it iterates down all the way through these lines, and it searches for matching against this format. And then it parses in the first residue ID, the second residue ID, and then the base pair type. And it pushes that into an array and returns all of that. Next is the load AJAX file function. So this takes in the URL that it's loading. It also takes in the callback and then the file type and the context from which it was called. So you shouldn't have to call this function. You should just be able to call the load file function. But just in case, if you need to add your own loading the files, then the way you do that is first you make this object that will let you send requests, like GET requests or POST requests. And then you open a GET request to a certain URL, and that URL is what's been passed to the function. And then you set it to plain text, and then you send the request. And if you want to send a POST request, then you would send the data inside the send function. And the most important part of this object is this onReadyState change function. So inside this function, we want to see if we're done and if the request has been successful. And if so, then we have to call the callback, since otherwise there's no way to return a value. So you need to pass it directly to this callback function. Next is the parseStat function. So again, this is pretty similar to the parseDSSR function, except we're just looking for a line of this format, and then we parse in the origin, the x-axis, the y-axis, and the z-axis. So the origin is the center, x, y, z are the rotation, and then we make a new base pair object with this residue information and this rotation and this origin, and then we return all of that information. So parse PDB is the main function of the PDB parser. So let's see, first we parse in model commands and end model commands and create a new PDB model for each of those. So as I said before, since we're only using the first one, this doesn't matter anymore, but the PDB parser will still send the information anyways. It's just discarded. We also parse in atom and we also parse in atom statements and get all of the information in the columns, such as the XYZ coordinates, the residue ID, etc. And then we also parse in the connect statements. And then afterwards, we create the bonds inside each residue. We create bonds between residues. And this also includes creating the backbone. And then finally, we generate the sequence. So this function basically just takes in the contents of the dat file. So that's this unique motif data. And then just parses each line into the various motif entries. Okay, so these are the basic utility functions for manipulating atoms and bonds and all of that. So first is just a basic function to create a bond if it doesn't exist already, if the hash doesn't exist. Next is a function to check the distance between two atoms. So these are the PDB atoms where their XYZ coordinates are stored in position 4, 5, and 6. Next is a function that just searches all of the atoms based on a residue name and atom name, and one that finds an atom based on its coordinates. And this one does the same thing. It searches for an atom in a given list of in a certain list of atom objects inside a residue. And then this is the hard-coded scoring function for the P4, P5 tutorial. So it just calculates the distance between the target end and the end we're currently at, and then it returns that. So it doesn't take into account the orientation. Whereas this function calculates the distances, and then it also calculates the orientation difference using the rotation matrices. And the isValidSolution function, it updates the HTML display, and it also calculates the score either using the normal scoring function, or if it's the P4, P5 tutorial, then using the hard-coded scoring function. And it checks to see if the score is less than some threshold. So this threshold is 7 for the normal puzzles and 1.5 for the tutorial. And if so, then the solution is close enough and you have a valid solution. The calc distance function just calculates the distance between 2 points. Each point is an array with XYZ coordinates at indices 0, 1, and 2. And then this one calculates the distance between two residue object atoms. So these are different than the points in the normal type of atoms because their XYZ coordinates are in positions 2, 3, and 4. So these can be changed. there's actually three functions to calculate the distance between 2 points, so they should be changed at a later point. Next, there's a function that just simply calculates the center of a list of atoms. And then there's a function that checks if there's a clash between the target end and the end that we're currently at. And it just checks if there's a distance less than 2 between them. Next, we have a function that aligns a newly added motif to the previous motif. So this is mostly from the Python version of the code. And first we save the old coordinates, we applied this new rotation, and then we applied the previous rotation of the previous motif. We applied the new translation, and then we modified the actual game objects, offset the atoms to account for the sugar differences, and recalculate the transform object, and then return everything. So next is anything related to the ghost motifs and the ghost hints, the already pre-computed possible solutions. So this just goes through the motif entries and it finds the new rotation and new position, and it returns everything into an array that contains the rotations and the positions and the name and the bend angle. Next, we have a function that just goes through the game objects and either sets them as true or false for visibility. And this is just a utility function that splits an array into chunks, splits an array A into n chunks. Afterwards, we have this function that first it removes all of the molecules, the game objects, and then adds them in into their new positions, and then depending on what type of ghost index we have, then we display certain ones, and then we add it to our starting index. So this function just gets the list of positions and then it sorts based on bend angle, splits them into chunks for the num keys 1 to 5, and then for each of these chunks it makes the plane, vectors vec1, vec2, vec3, and vec4, makes the sphere, and it draws the plane, draws the sphere, and then it also, so there's two spheres. There's the sphere that's displayed, and then there's the sphere that you can click on that's not displayed. This is just for mouse click collision checking in the game. So next we have everything related to the sequence and secondary structure generation. So as I said before, this is pretty hacky right now, so this will need to be modified at a later date. So first we have this generate merged motif function that calculates the sequence and the secondary structure. Yeah, so it's pretty hacky. And now there's this get secondary structure command that is just called from the generate merge motif, and it gets the secondary structure based on the base pair type. Next is a function that compares two base pairs and checks if they're the same by seeing if the distance between their atoms is greater than 0.01. And then it's the same thing except for two residue objects, comparing to see if the distance is less than 0.01. And this just checks if it's a Watson-Crick base pair, and if it's between guanine and uracil. This one converts the the chain of residue IDs to actual residue objects. And this one finds a residue on an actual chain. So next are some utility functions that are used to help manipulate the matrices and vectors. So first, a function to transpose matrix, and this returns the modified matrix. And then this function multiplies two matrices, and they can be of any size. And again, it returns the modified matrix. So this function multiplies a vector by this function multiplies a vector of 3 elements by a 3x3 matrix. So the first parameter is the vector, and the second parameter is the matrix. And then it returns the modified matrix. And then this function subtracts two vectors, it doesn't subtract matrices. And the naming is just because when I was converting it over from NumPy, I thought this was initially going to be the matrix function, but this should probably be changed to subtract vectors v1, v2 instead. Next, this subtracts a vector from a matrix. So it's the vector has 3 elements, and the matrix should be a 3x3. And then this is the same thing except for adding. Okay, so now is the code that's related to displaying game objects using the 3JS library. So this just interfaces with WebGL for us. So instead of having to use the shaders and go into all of the code just for displaying 3D, we can instead use the built-in objects. So first is a function that it first loads in the container from HTML, and then it creates the camera object, creates the 3JS scene, loads the ball for the atoms, creates the WebGL renderer, creates the controls for when you're using your mouse, sets the position of the camera, and then loads the puzzles based on which puzzle we're on right now. Afterwards, it adds the event handlers for when the window resizes, when we should resize the game window, and when we click or move the mouse. So that's for checking click and double click on atoms. Next, we load the unique motif data for the pre-computed solutions, and we render, and we call the animate function. So this is the load molecule function. This is another one of the main functions. So first we set all of the progress variables to incomplete. So this way, if we try loading 2 molecules at the same time, one of them will wait until done loading becomes true. And we also create a new model that stores in all of our game objects. And to determine it, based on the path, we determine whether or not it's a helix. And if it's not a helix, then if it's part of the main puzzle or if it's a normal motif. So 2 means it's a helix, 1 means it's part of the main puzzle, and 0 means it's a motif. And we set the path for the model name. So this is for when we're doing the used motifs list. And then we load the file and we pass in a callback function. And the callback function just initializes the materials, creates the residue objects, centers the molecule, loads in the bonds and the chains, updates the lengths, and creates the actual bonds, loads the atoms, creates the actual atoms, and then displays everything. And then we also have our second callback function that just uses handle data. So because the PDB callback, the DAT callback, and the DSSR callback can be called at different times, we need a way to check when all of them are done. So that's this handle data function, which will wait until all three functions have been called. And the way we check that is this loaded DSSR and loaded PDB. And then this is our third callback, which just sets loaded DSSR to true, and then sets the data for the model object to the data that we loaded in. So afterwards is the handle data function that I was talking about before. So it waits 100 milliseconds each time until all three files are loaded, the PDB file, DSSR file, and the reference series file. And then once they are loaded, it converts the residue names inside the base pair objects to actual residue objects based on the residue IDs. And then it combines the residues for the atoms from residue 1 and residue 2 for each base pair into an overall atoms list. And then makes the base pairs to this loaded data that we were modifying before. It creates the base pairs, adds the DSSR information, and then resets the ghost molecules depending on what type of puzzle it is. And then if we're not at the first molecule, if we're not just loading the tetraloop receptor or FMN PDB, then we try aligning, and while there's a clash between the molecule that we're trying to align and the previous molecule, then we reset everything and try aligning again on a different base pair ending. And if we can't align, then we just give an error message. But if we can align, then we render the model and we set the previous transform of that model to what we get from the align function, and then we reset the ghost molecules again. Afterwards, we check if there's a valid solution, and if so, then we check first if it's the tutorial, then we just return and say that since you can't submit solutions on the tutorial. Otherwise, we generate the sequence and secondary structure and update the HTML interface. So next is the function that renders the models. So it renders the atoms, it updates the positions of the bonds, it modifies the location of the backbone bonds, and it updates the location of the collision spheres. So these are the four main game objects: the collision spheres for when you're clicking, the atoms that you're displaying, the bonds that you're displaying, and then the backbone bonds that display the overall structure. So now is the animate function. So first it calls this request animation frame function. That just keeps a steady frame rate going. Then it updates the controls so that based on what we did with the mouse, such as moving around the screen, the actual game view updates as well. Then we calculate how far zoomed in we are and update the line width accordingly. And we make the starting positions flash. And finally, we adjust this interface with the position that we're at. So this function just undoes adding a molecule. So first we remove it from the overall game objects array, and we remove the atoms and backbone bonds from the scene. And then for each of the collision spheres, we remove them, and for each of the bonds, we remove them. And then we just update the interface again. So this function is called when the submit button is clicked. So that's not this one, but so it's called when the submit button is clicked. So first we check if the username is empty, and if so, then we return, since we can't accept empty usernames, and then we also check to make sure that the solution is valid. After that, we generate the sequence and secondary structure and submit everything using the same XML HTTP request, except this time we're using a post request instead of a GET request. And we send in all of this information using this form data object that we put into the send function here. So now are some functions for updating the game display and the HTML interface. So this function just, depending on whether we're displaying atoms, bonds, or both, it just it toggles their view so that it updates properly with this control. Next is this function that updates the coloring of the overall molecule. So that's between the GUAC coloring and the grayscale coloring. That's based on molecule. This function just toggles the backbone based off this. So if the backbone type is 1, then we add it, otherwise we remove it. Alright, so those are all most of the main functions. There's still some other functions that are pretty minor for just for like updating the interface, such as this used or this part, and also the WebGL detector. But you can still check out most of the code in these slides. And you can also, so I'm going to click back to function groups after this and then just wait 20 seconds on each slide so you can see the code. And then you can also check out the issue list on GitHub. So this has all of the issues, the feature requests and bugs, and it also has the list of motifs because some players wanted to check those out, the PDB files. So it's just Fiend SK1 and then Eterna 3D. And then there's also, you can see the original code on the Bitbucket page. Just send me a request and I'll add you to it since it's a private repository. So this one is a little different. So all of the code is in code/new final, and then so you can see the styling for the HTML interface in CSS/. You can see the images, the puzzle image and image. You can see the main JavaScript code, so that's the PDB parser and the code for creating this header, the code for creating this sidebar, and then the code for creating this toolbar. Lib contains all of the external libraries, so livepipe.js for hotkeys and this scroll bar, and 3JS for interfacing from WebGL to this 3D display. Motifs contains the PTB files. Solutions contains the solutions people have submitted. This you can ignore. This you can also ignore. Game P4, P5 is the most updated, so if you want to change the game type in that, you just need to change this puzzle name from P4, P5 tutorial to Tetra Loop Receptor Puzzle or FMN Puzzle. Index.html is for testing merging, and unique motif data is the pre-computed solutions. Alright, so that's pretty much it. If you want to stick around and check out the code, then you can do that, otherwise you can just close this video now. So if you want to see the code for any of these slides, then just pause, click the pause button on them, and yeah. Okay, if you have any questions, you can just email them to me at finitesk1@gmail.com. It might take me a bit of time to respond since I'll be at school, but I'll get back to you in a timely manner. Okay, thanks for watching.